So this is one way to understand this algorithm. Here is another way. So we will look at some linear algebra. So let's say enter linear algebra now. For those who are familiar with linear algebra, maybe you are already seeing these connections. Nevertheless, I will try to explain it now. Right. So now we did talk about this briefly last time, but let's make this more precise now. Right. So this is the problem that we are trying to solve, where C is 1 over n sum over I xi transpose, and the C is called the covariance matrix, with some caveats, but covariance matrix in general. And when you have a matrix like this, the solution to this problem is nothing but the eigenvector corresponding to the largest eigenvalue of this matrix, right. So the solution to this problem turns out to be W1, which is the eigenvector corresponding to the largest eigenvalue. Eigenvalue of C, right. So yeah, so this this comes from a general theorem which is called the Hilbert's min-max theorem. I'm sure if you had taken a linear algebra course or the foundational course, so you would have encountered this at some point, or a variant of this theorem, right. So this is from that. In fact, more is known, right. So Hilbert theorem says more, right. So in fact, not just W1, you can go ahead and find out W1 to WD, right. So the eigenvectors of C, form a orthonormal basis. So the orthonormal basis of interest for us, which does the error minimization, happens to be of centered data, happens to be just the eigenvector basis of the covariance matrix. That's essentially the takeaway from the linear algebraic point of view, one takeaway. Now this Wk, the kth eigenvector, or the eigenvector corresponding to the kth largest eigenvalue, is exactly the best line one obtains after round k, in round k rather. So the previous procedure that we said, where we go one step at a time to get these w's, in the kth round you will get wk, and that wk is exactly same as the wk that you would get if you did this, right. So this is again a conclusion that you can derive from Hilbert's min-max theorem, that if you try to maximize this it's the same quantity, where you want W to be norm 1, but then W should be orthogonal to an already existing subspace, well then that subspace is formed by the top k minus 1 eigenvectors, then the Wk would be the kth eigenvector. That's also Hilbert's min-max theorem, but we can either understand it that way, or we can simply say that this is the line that you get in the round k. Remember, the line that we got in round k will by definition be orthogonal to the previous lines, because the data set that we used were all orthogonal to the eigenvectors to the lines that we derived in the previous rounds by construction. Okay. Fine. So this is fine. So we can think of this as eigenvectors and eigenvalues of the covariance matrix, but what does it even mean, right? So what do the eigenvalues mean? What do eigenvalues of C mean? Can we say, can we interpret this slightly differently, or we should just be happy to say that these are eigenvalues of C, right? So that's fine, but then that does not really tell us anything more than the fact that it's a known, well studied object, right? So can we say something more? Can we think of this in a more geometric point of view? Well, let's try, right? So we know CW1 equals lambda 1 W1, where CW1 is the eigenvector and lambda 1 is, let's say, the largest eigenvalue, right? So corresponding to eigenvector W1. Or in this this works for even general Wk, where lambda 1 will be replaced by lambda k, but for now let's start with W1. Now what is W1 transpose CW1? Well, that would be W1 transpose lambda 1 W1, that would simply be lambda 1, because W1 transpose W1 is 1 by our definition of looking for lines with unit length. So, lambda 1 equals W1 transpose C W1, which is equals W1 transpose 1 over n, sum over I is 1 to n, xi transpose, that is your C, times W1, which is just sum over I equals 1 to n, xi transpose W1 squared. So, now this term must be this is lambda 1 and this term must be familiar. So, this is exactly the term we used earlier, right. So, where did we use it? Well, we used it to find out how many rounds we should run this algorithm for, right. So, this is basically, this term is exactly the the eigenvalue, the highest eigenvalue. So, so now basically then we can do the following. I mean, whatever we did last time, I mean before, can also be interpreted like this. So, you have k, which is the number of rounds or the kth eigenvalue, and let me put it small k, and now you have lambda k of the covariance matrix, and if you plot that those guys are going to fall down, right. So, our lambda I k of C is the kth largest eigenvalue of C, because this is exactly the the term that we used earlier too. So, now the rule of thumb, right. So, rule of thumb for how many dimensions, for number of dimensions last time, like how we just said like a few minutes back, would be to look at the following quantity, sum over I equals 1 to sum k, or so let us call this sum L lambda I of C divided by sum over I equals 1 to D lambda I of C. If this ratio is greater than or equal to 0.95, usually in practice, this is a thumb rule, usually in practice, then we are saying that, well, we are retaining some 95% of the information in this data set, right. So, that is the general idea. Now, for this quantity to make sense, right. So, summing up the top k, top L and then dividing it by the entire thing to be greater than 0.95, all of these have to be positive values or at least non-negative values, right. But then that is true because of the fact that your lambda 1 and in general lambda k will be sum over I equals 1 to n xi transpose wk squared. So, this will be just an average of a bunch of square terms. So, all of this will be positive. So, in fact, this covariance matrix, this kind of tells us that the covariance matrix has non-negative eigenvalues, which means the covariance matrix is, for people who have seen this, is a positive semi-definite matrix, right. So, this is also a proof of that. Anyway, so the main point is that this quantity makes sense, right. So, because these are positive numbers. So, you can look at the ratio and see when it crosses 0.95 and then use that as a value that you want. Okay. So, this is fine. So, what we are basically doing is that we are saying that we are maximizing the quantity that we are maximizing is actually the eigenvalue of the data set that we, so of the covariance matrix of the data set. But that still does not tell us what this quantity is, right. So, it just explains us the quantity's equation in terms of eigenvalues, right. So, but that does not really tell us what is this quantity about, right. So, can we understand this quantity in a more simpler way, specifically this quantity? I mean, of course, it happens to be the eigenvalue of the covariance matrix, that is well and good, but what is it, right. So, can we say anything about this term? Okay. So, now let us say we take again a bunch of data points and a line, right. So, maybe there is an x1 and then this point becomes x1 transpose w into w and so on. Maybe there is an x2, it becomes x2 transpose w into w and so on. Now, let us say we, for a fixed w, we collect these values x1 transpose w, x2 transpose w dot 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 xn transpose w. Let us say we collect these values, right. So, these are like the in some sense if you square this, there will be the length squared of the projection, the proxy for each of these data points on the line W, right. So, I am not saying the line W is the best line or anything, it could be any line, and then we are collecting this bunch of data points. Now, the first question is, what is the average of these values? Average. What would this be? Sum over I equals 1 to n xi transpose W. I am not saying anything about W being the best line or anything. Pick some arbitrary line and then project onto that line, compute these xi transpose W values and then compute their averages, right. So, what is this value going to be? So, if you may want to pause and think about this before I tell you the answer now, right. So, this value is just 1 over n sum over I equals 1 to n xi transpose W Now, this value for a centered data set, this value is just the mean, but then the mean is 0 for a centered data set, right. So, we are assuming that the data set is centered. So, this is a centered data set. Now, what does that mean? That means that the average is actually 0 for a centered data set, right. So, this is it's a number, it's 0. Now, fine. So, now what can we say about the same set of values, but then let us look at the variance, right. So, how much spread is there in this bunch of values? Now, how would we compute the variance? Well, we can do it this way: 1 over n sum over I equals 1 to n xi transpose W minus the mean squared, where the mean or the average is the average of this bunch of numbers. But we know that the mean is 0. That is what we just looked at. So, which means this value is just going to be 1 over n sum over I equals 1 to n xi transpose W squared, right. So, what is this telling us? This is telling us that you pick an arbitrary W and then project all your centered data points onto this W and then just compute the variance of the projected values. Now, that variance is exactly the term that we were using earlier, right. So, it is exactly this term that we are trying to maximize, and it is exactly the term which is equivalent to the eigenvalue, right. So, now this is interesting. So, now at least we know, what are we doing when we are doing this maximization, right. So, basically then we can conclude the following, right. So, error minimization, which is what we started this algorithm with, on centered data, right. So, the centering is important because only then the equivalence that we are putting out now holds, is equivalent to variance maximization, right. So, if you find a line where the error is minimum, then it also means that it is the same line where the variance of these projected values is as high as possible, right. So, to see why this has to happen geometrically, of course, algebraically we have seen this, but then geometrically also you can kind of convince yourselves that maybe you have a bunch of points like this, and maybe the green line is the best line. Maybe there is also this maybe there is also this blue line. Now, you could project it onto either of these lines. If I project it onto the green line, I am going to get the proxies as follows, right. The green dots are my proxies, whereas if I project it onto the blue line, the blue dots are the proxies of the red points, Now, if you focus on the green points, you can see that they are kind of spread out than the blue points which are crowding up, right. So, now the problem is if data points all crowd up, in fact, if they go to the same point, then there is no way you can distinguish this one data point from the another. Whereas, if they are spread out, then this distinguishing capability is still present in this data points. You do want compression, but you also want to be able to distinguish one data point from another, because in downstream you are going to use this compressed representation for some other task, let us say supervised learning, then you still want to say one data point from the another, right. So, the distinguishing capability is still necessary, which is lost if you project it along a wrong line, right. So, a wrong line where all the data points crowd closer to each other, which means if the variance of the projected data points is small, then that is a problem. In fact, if all data points actually fell on the same line, now if you look at the perpendicular line and then think of that line as your actual line, then what would happen is all the data points would project onto the 0 vector, which means that there is no way to distinguish one data point from another, and that is a bad thing, right. So, because you cannot really use this representation to do much later. So, what you really want to do is you want to find directions where the projections do not crowd up, right. So, we want directions where projections do not crowd up, right. So, I am using this crowd up in a loose fashion, but for us the definition of crowd up is that variance that is variance is not small, right. So, we want variance to be as high as possible, and in that case we would have found a line where the spread is as high as possible. In other words, the information retained is as high as possible, right. So, that is one other way to think about PCA itself, right. So, this algorithm itself, of course. So, this is one way to think about it, and there is one more example that we will see, and then we will conclude this initial algorithm that we are starting to look at. Probably I will use this here. Here is one way to understand what is happening, right. Let us say we are given again a bunch of data points centered and so on, and let us say this is the height and this is the weight, they are centered. So, that is why you see negative values. So, let me put it centered, centered, and so on. Now, if the main thing that we are observing is that height gives some information about weight, right. So, if I tell you what the height is, right. So, if the height increases, the weight also tends to increase, right. So, that is the main observation here, and that is why we started with fitting lines and so on. But more importantly, height and weight are not completely loosely saying independent of each other, right. So, I should be careful when I use the word independent, but let us say intuitively height and weight are not independent of each other, because height gives me some information about the weight, right. So, so if I choose to represent these data points as height and weight, as two numbers height and weight, then one number gives me some information about the other number. Now, if I did this algorithm where we find these lines, right. So, let us say we found this line, which is the best line, and this line W is going to be 1 1. Well, of course, it can't be 1 1 because it has to be of length 1. Let us say I normalize this and the length is 1 by square root 2, 1 by square root 2, then it means that the first, so if I am allowed to use only one number to represent each data point, then that number would be the dot product of each data point along this direction. Well, the data point itself is just height and weight. Now, this direction is 1 over square root 2, 1 over square root 2, which means that what I would actually be storing is the value height into 1 over square root 2 plus weight into 1 over square root 2, which is height plus weight over square root 2. Now, for whatever reasons, if I went ahead and found the second line, right, so which would fit the error vectors, it would be along the perpendicular direction, we know that, and that vector would simply be minus 1 1 normalized, that would be minus 1 by square root 2, 1 by square root 2. Now that axis, right, so that value, projection along that value would be minus height plus weight, or rather weight minus height by square root 2. It could be height minus weight by square root 2 also. If I think of that vector as 1 by square root 2 minus 1 by square root 2, doesn't really matter, right. So, it can be either. So, if I now thought of plotting the same data set, but then by thinking of these two axis values, right. So, instead of height and weight, I am going to compute two numbers, height plus weight over square root 2 and weight minus height over square root 2, and then plot the same data set. How do you think that data set would look like? This is a good place to pause and think. Let me tell you how the data set would look like. The data set would look something like this, right. So basically what has happened is, you can think of it as if this height axis got transformed, rotated, in this case by 45 degrees to get this height plus weight by square root 2 axis. Of course, there is a scaling happening, which I am not indicating here, but yeah, I think you can imagine that, right. So, and the weight axis has gotten rotated this way to become weight minus height by square root 2. Now, if I think of looking at the same data set in this direction, well, that would exactly look like this, right. So, if we plot that. Now, what is the point here, right. So, what is the point of plotting this? Well, this is telling us that, well, now if I told you the x axis value, which is height plus weight over square root 2 value, there is nothing that you can really say about weight minus height by square root 2. If height plus weight by square root 2 increases along this direction, there is nothing really happening for weight minus height by square root 2. It can either be above the axis or below the axis, but then there is no real pattern there. Whereas in the previous case, as height increased, the weight tend to increase, and if height decreased, the weight also tend to decrease. Here nothing like that is happening, right. So, in other words, height plus weight over square root 2 does not give any information about weight minus height by square root 2, right. So, well, in other words, these two directions, right. So, the W1 and W2 directions, and then the values that we project onto these directions. So, the terminology is that these directions are decorrelated for this data set, right. So, the directions where every direction gives you some new information that the previous directions are not giving you, you are trying to find those directions, right. So, that is what our algorithm is essentially doing, and this algorithm, well, is called the principal component algorithm. You might have come across this algorithm already if you had taken a MLF course. Nevertheless, we thought it would be good to start with this algorithm, because some of the ideas that we will see now, which you may not have seen in the MLF course, would lead us to something more fundamental in machine learning. And the W1s to Wk that we have managed to find, these vectors are called as the principal components. And what our example now says is that these principal directions are in fact decorrelated, right. So, the projections along these directions kind of are decorrelated. So, essentially the algorithm is, given the data set, find the covariance matrix, find the top k eigenvector and eigenvalues, project your data set along the eigenvector directions, and then that would give you a compressed representation. Because we are going from Rd to Rk, where k might be much smaller than d, this is also a dimensionality reduction technique, right. So, our essential dimension that we believe for this data set is only k, right. So, the top k eigenvectors, which constitute to 95% of the variance. It can explain 95% of the variance in our data set. That is why the 0.95 that we used, where I said its information is essentially the amount of variance explained by the top k eigenvectors. So, we should think of each of these directions as a dimension essentially, and what PCA does essentially is now finding new axis, right. So, PCA finds combination of features, right. So, by when I say xi transpose w1, it means that you are weighing these features in xi using the weights given by these eigenvectors, right. So, it finds combination of features that are decorrelate. Loosely speaking, independent of each other. So, this is a very fundamental algorithm in data science, in dimensionality reduction and so on, and one of the basic algorithms that we will start with for representation learning. So, next time what we will see is one simple example where this algorithm can be applied, and this example is called as the eigenfaces example. So, a face recognition type of a system that you can build using the principal component analysis algorithm. We will demonstrate that, at least show you some pictures. That is the first thing. And then what we will do is we will identify some potential issues with PCA and places where it may not necessarily work that well. And once we have identified those, we will try to fix them. And as in the matter of fixing them, that will reveal to us some interesting insights about how to look at data set, what is important in a data set and so on. Which will lead us to more foundational ideas in machine learning. So, all that will come in the next few lectures. For now, we have seen PCA, and I hope you are able to appreciate the fundamental nature of this idea and this algorithm. Thank you.